Is the universe going to collapse soon? The prevailing cosmological narrative of the last century has been one of a cold and infinite expansion, a universe marching inexorably toward a silent and frozen heat death. However, a surprising new cadence is emerging from the latest data, suggesting a profoundly different and dynamic ending. To understand this paradigm shift, it is necessary to first reimagine the fundamental nature of the cosmos, moving away from the view of a static machine composed of gears and levers, and approaching a vibrant and resonant entity analogous to music. Theoretical physicist Michio Kaku, one of the co-founders of string field theory, has long postulated that the universe is best understood through the language of harmony. In this view, the subatomic particles that make up the fabric of our reality, quarks, electrons, neutrinos, are not rigid, point-like objects, but rather different modes of vibration on tiny oscillating strings. Physics, in this grand analogy, becomes the laws of harmony governing these vibrations, while chemistry is the melody played when these strings interact. The universe, in its totality, is a symphony of strings vibrating in an 11-dimensional hyperspace, and what has been poetically termed the mind of God would be cosmic music resonating through this hyperspace. For decades, the scientific community operated under the premise that the conductor of this symphony, the mysterious force known as dark energy, was accelerating the tempo of the music forever. The standard model of cosmology, firmly established in the late 1990s, suggested that dark energy was a constant and immutable force, pushing galaxies away from each other with ever-increasing speed. Under this regime, the tension of space-time would remain high, driving an eternal expansion that would eventually tear the music apart, silencing the symphony in a big freeze or heat death. However, the latest and most precise data collected by humanity's giant robotic eyes suggest that the music is changing key. The tension is decreasing. The symphony, it seems, is slowing down. This revelation is grounded in understanding dark energy not as a rigid constant, but as a dynamic field capable of evolving over time. If the tension of space acts like the tension on a cello string, a constant dark energy keeps that string taut, ensuring a fast-paced, high-pitched expansion. However, findings from the Dark Energy Spectroscopic Instrument, DESI, imply that this tension is undergoing a process of thawing or relaxation. The force driving galaxies apart is losing vigor. If this trend confirms and continues, the repulsive force that has dominated the universe for the last few billion years could diminish and eventually reverse. When the cosmic music ceases its acceleration and begins to decelerate, the universe will enter a new movement, collapse. This establishes the central scientific mystery of this narrative. Why is the music changing? The answer may lead to the terrifying and majestic possibility that the symphony will not end in silence, but in a crescendo of fire and light known as the Big Crunch. The narrative of the Big Crunch is reborn with the dismantling of the most established pillar of modern cosmology, the cosmological constant. Since the historic discovery of cosmic acceleration in 1998, the standard model of cosmology has been referred to as lambda CDM. In this model, the Greek letter lambda represents dark energy, conceived as a repulsive force inherent to empty space itself. For 25 years, it was assumed that this force was constant over time, meaning that as the universe expanded and created more space, the amount of dark energy remained uniform, exerting the same relentless pressure per cubic meter. This assumption was mathematically encoded in the equation of state of dark energy, where the parameter $W$ was strictly fixed at -1. This value indicated a constant energy density that would drive the universe into an eternal and accelerated expansion, leaving humanity isolated in a dark and cold void. However, in April 2024, a seismic shock ran through the scientific community with the release of the first year of data results from the Dark Energy Spectroscopic Instrument, DESI, collaboration. When these new high-precision data were combined with existing datasets from the Cosmic Microwave Background, CMB, and supernovae observations, the results showed a statistically significant deviation from the standard lambda CDM model. The data no longer favored a static cosmological constant. Instead, they pointed to a model where dark energy is evolving. The equation of state is now modeled with two parameters, $W_0 and $W_, to account for this change over time. The surprising conclusion drawn from the data is that the parameter $W_, appears to be negative, suggesting that dark energy was stronger in the past and is weakening or thawing in the current epoch. The statistical significance of this discovery is profound and cannot be dismissed as a mere fluctuation. In the world of high-energy physics and cosmology, a result is often considered provisional until it reaches a high-probability threshold. The DESI results, when combined with other large datasets, push the significance level to between 2.5 sigma and 3.9 sigma. This translates to an extremely high probability that the deviation is real, representing the strongest evidence against the standard model in 25 years. Visually, this can be interpreted as the Greek marble pillar of the cosmological constant, which held up the sky of our understanding, beginning to show structural cracks. If dark energy is indeed weakening, the acceleration of the universe is not guaranteed to last forever. Gravity, the long-range attractive force of matter, has been waiting patiently in the wings. As the repulsive push of dark energy diminishes, gravity may once again gain supremacy, pulling galactic structures back toward one another and initiating the collapse. The credibility of this paradigm-altering revelation rests entirely on the engineering marvel that made it possible. The Dark Energy Spectroscopic Instrument, or DESI. Located at the Kitt Peak National Observatory in Arizona, DESI is mounted on the Mayall telescope, a massive structure that was retrofitted to become the most advanced time machine ever built by human hands. The instrument does not merely take photographs of the sky. It analyzes the chemical fingerprint of light from millions of distant objects to determine their precise distance and speed. This capability allows astronomers to look back in time and map the history of the universe's expansion with unprecedented precision. The mechanism at the heart of DESI is a technological hive mind composed of 5,000 robotic fiber optic positioners. These are not large industrial robots, but delicate actuators, the size of a pencil, packed densely into the focal plane of the telescope. Each robot is capable of independent movement, positioning a fiber optic cable with an accuracy of 10 microns, a fraction of the width of a human hair, in a matter of seconds. Every 20 minutes, the telescope points to a new patch of sky, and these 5,000 robots perform a synchronized dance, locking onto 5,000 individual galaxies or quasars simultaneously. The light collected by these fibers is then channeled into a bank of spectrographs, which split the light into its constituent colors, revealing the redshift of the galaxies and, consequently, how fast they are moving away from us at that specific point in cosmic history. Through this automated process, DESI has created the largest and most detailed three-dimensional map of the universe ever constructed, cataloging over 40 million galaxies and quasars. This map effectively allows scientists to fly through the cosmos, receding back in time more than 11 billion years. The primary target of this mapping effort is the measurement of baryon acoustic oscillations, BAO. These are, in essence, frozen sound waves left over from the Big Bang. In the hot, dense plasma of the early universe, pressure waves traveled through matter, creating slight overdensities that eventually seeded the formation of galaxies. These waves have a specific and known length, acting as its standard ruler for cosmologists. By measuring how large these standard rulers appear at different distances on the DESI map, scientists can chart the expansion rate of the universe across different epochs. It is this precise measurement of the fossilized sound waves from the Big Bang that revealed the potential weakening of dark energy. If dark energy is not a fixed cosmological constant, physics demands a new candidate to explain the acceleration we observe, and the leading alternative is a concept known as quintessence. Unlike the rigid lambda of Einstein's equations, quintessence is described as a scalar field, a dynamic energy field that permeates all of space but can change in value and distribution over time and space. The behavior of this field determines the ultimate fate of the universe, and the new data suggests a specific type of behavior that aligns with the Big Crunch scenario. Cosmologists categorize quintessence models into two broad classes, freezing and thawing. In freezing models, the field was rolling rapidly in the early universe and has since slowed down. However, the DESI data favor the thawing model. In this scenario, the field was frozen by cosmic friction in the early universe, like a ball stuck in a high valley. Recently, in cosmic terms, this field thawed and began to roll downhill in its energy potential. As it rolls, its kinetic energy increases and its equation of state changes. This dynamic nature implies that the energy density of the vacuum is not fixed. The implication of a thawing quintessence is dramatic. If the field rolls far enough down its potential, it can cross into a regime where the vacuum energy density effectively becomes negative. This transforms the repulsive force into an attractive force. Unlike the Big Rip scenario, where dark energy becomes stronger and tears atoms apart, a phantom energy scenario, quintessence allows the force to weaken and reverse. If the field rolls to a negative potential, the force currently pushing galaxies apart will transform into an attractive force, adding to the gravitational pull of matter. This would act like a cosmic rubber band that was stretched to the limit and is now snapping back, bringing fire and light. With the mechanism for collapse identified as thawing quintessence, physicists began to calculate the timeline for this cosmic reversal. Based on the new parameters provided by the DESI data, specifically the values of $W_0 and $W_$, a team of physicists including Henry Tai, Hongnan Liu, and Yuqing Qiu modeled the future lifespan of the universe. Their calculations provide a stark contrast to the previous assumption of a universe that would last for trillions of years or essentially forever. We are, according to these models, living in the middle age of the cosmos. Mathematical models suggest that the current age of the universe, approximately 13.8 billion years, places us just a little before the peak. Expansion is not infinite, it is finite. Calculations indicate that the universe will continue to expand for approximately another 11 billion years. During this phase, expansion will slow down as the scalar field of dark energy rolls down its potential and the repulsive force diminishes. The universe will reach a maximum size, or turnaround point, which is estimated to be about 1.7 times its current scale. This means the cosmos will not get significantly larger than it is today before the mechanics of expansion fail. After the turnaround point, the universe will enter a contraction phase. Gravity, no longer counterbalanced by dark energy, will begin to pull the fabric of space-time inward. This contraction phase is estimated to last for another 20 billion years, leading to a total lifespan for the universe of approximately 33 to 34 billion years. This discovery fundamentally alters our perception of our place in time. We are not at the dawn of an eternal cosmos. We are mid-journey. The end is not a distant abstract concept situated at infinity. It is a concrete event with a calculated date. The universe is like a ball that has been thrown upward. We are currently observing it just before it reaches its maximum height, apogee, where it stops and, inevitably, falls. As the universe transitions from expansion to contraction, the visual experience of the cosmos will undergo a terrifying transformation, governed by the physics of light and the Doppler effect. Throughout human history, astronomers have observed redshift, the stretching of light waves as galaxies move away from us. In a collapsing universe, this phenomenon reverses. We will witness blueshift, where light from distant galaxies is compressed as they approach us, shifting to higher frequencies and shorter wavelengths. This change is not merely aesthetic. It is a massive increase in energy. According to the physics of electromagnetic radiation, shorter wavelengths carry more energy. As the universe contracts and the scale factor drops, radiation density skyrockets. Light that was once visible and benign will shift to ultraviolet, then to X-rays, and eventually to gamma rays. This phenomenon is known as the violet catastrophe. Initially, the night sky will change as the darkness between the stars begins to glow. The cosmic microwave background, currently invisible in the microwave range, will be blue-shifted back into the visible spectrum. The intensity of this light will grow exponentially. Every point in the sky will eventually be filled with the light of an approaching galaxy, or by the blue-shifted background radiation. The night sky effectively vanishes, replaced by a blinding, uniform glow. The darkness of space, which has been the backdrop for all stellar evolution, will be abolished. Radiation density will become so high that it will start to interact destructively with matter. Adapting Michio Kaku's analogy about dimensions, the waves of light are crashing back onto us, building a tsunami of high-energy photons. The contraction of the universe brings with it a thermodynamic revolution that makes life impossible long before the final singularity. The cosmic microwave background, CMB, which is the fossil heat left over from the Big Bang, has cooled over 13.8 billion years to a frigid 2.7 Kelvin. It is this cooling that allowed the formation of structures and the evolution of life. However, in a contracting universe, this process reverses. The compression of space-time acts like a piston, compressing the photon gas and raising its temperature. As the universe shrinks, there will be a brief period known as the second habitable zone. When the universe contracts to about 1,000th of its current size, the CMB temperature will reach approximately 300 Kelvin, room temperature. Physicist Avi Loeb describes this as a period where space itself is warm. You wouldn't need a sun to keep warm. Liquid water could exist in the void, allowing oceans to exist on rogue planets, far from any star, warmed only by the glow of the cosmic background. However, this habitable phase is fleeting, a prelude to the cooking. Within millions of years, the temperature will rise to 373 Kelvin, the boiling point of water, and then to 1000 Kelvin. Planetary atmospheres will be stripped away. Oceans will boil and evaporate. The universe becomes an oven. This cosmic greenhouse ensures that biological life cannot survive the crunch. Rocks will begin to glow red, and the universe will return to a plasma state, reversing complex chemistry back to fundamental elements. Before total thermal destruction, the mechanical contraction of the universe triggers chaos in large-scale structures. As the universe shrinks, matter density increases dramatically. Galaxy clusters, currently separated by vast voids, will be crushed against one another. The supermassive black holes at their centers will collide, ushering in the era of black holes. Matter density will increase to the point where galaxies are ground together. We will witness a frenzy of black hole mergers, creating a background of gravitational waves so intense that it will warp spacetime perceptibly. Eventually, black holes will devour the remaining matter and then merge with one another. The universe effectively becomes the interior of a single, colossal black hole. Event horizons will grow to encompass the entire observer, or rather, the singularity will move from the future to the present. The spaghettification, described by Neil deGrasse Tyson, ceases to be an individual destiny and becomes the destiny of the entire cosmos. Does history rewind? A famous controversy in physics involves the arrow of time. In early drafts of A Brief History of Time, Stephen Hawking suggested that time might reverse in a contracting universe, implying that entropy would decrease. Broken cups would mend, people would undie. However, Hawking later retracted this idea, admitting it was his greatest mistake. Entropy, disorder, continues to increase even during contraction. The implication is that the Big Crunch is not a movie played backward. It is a movie played forward into a furnace. The universe ends in a state of maximum entropy, total chaos, distinct from the minimum entropy, total order, of the Big Bang. Brian Cox's sandcastle analogy is perfect here. The wind blows the sandcastle away, but it never blows it back into the shape of a castle. In the crunch, the sand is not rebuilt. It is fused into glass by the heat. The form is lost forever. General relativity predicts a singularity, infinite density, at the end, where physics breaks down. However, quantum gravity theories, such as loop quantum gravity, suggest a bounce. At Planck scales, space becomes discrete, quantized, and cannot be infinitely compressed. Gravity may become repulsive, causing the universe to ricochet. Sir Roger Penrose proposes conformal cyclic cosmology, CCC, suggesting that the high-entropy end of one universe is mathematically equivalent to the low-entropy beginning of the next, due to mass loss and scale invariance. Penrose argues that Hawking points, ghostly rings in the CMB, are the scars of supermassive black hole collisions from the previous universe. The universe functions like a breathing lung. It empties in the crunch, pauses, and fills again in the Big Bang. It is the image of the phoenix rising from the ashes. To complete the scenario of cosmic endings, the Big Crunch must be distinguished from the Big Slurp, or vacuum decay. While the crunch is gravitational, vacuum decay is quantum mechanical. The Higgs field may be metastable. A quantum fluctuation could cause it to drop to a lower energy state, creating a bubble of true vacuum that would expand at the speed of light, incinerating everything and rewriting the laws of physics. The connection to the crunch is critical. The extreme pressures of the Big Crunch could trigger vacuum decay in the final moments, sealing the fate of the universe even before the gravitational singularity is reached. Unlike the crunch, which we see coming via blueshift, the slurp arrives without warning. One moment there are stars, the next, nothing. The stardust we are made of, as Tyson says, would have its fundamental laws rewritten, and matter itself would dissolve. If the universe is finite, this makes our time here infinitely more precious. Finitude offers a gift, the urgency and value of the present moment. Sagan reflects, Hindu sages wove myths of a universe that is born, lives, and dies, only to be born again. Modern science, with its great machines and fiber optic eyes, is finally catching up to this ancient poetry. If the Big Crunch is real, then we are not adrift in an eternal void. We are falling back into the embrace of the beginning. We are going home. The cosmos is all that is, or was, or ever will be, and perhaps will be again. Neil deGrasse Tyson also reminds us of our atomic connection to the cosmos. The Big Crunch is the ultimate recycling plant. It takes the atoms that were forged in the stars and returns them to the primordial fire. We are stardust, empowered by the universe to figure itself out. If the bounce theory is true, our atoms have been here before and will be here again. We are part of an eternal and cyclic cosmic dance.